name is Hansa, and I'll be the moderator of today's talk. I would welcome our speaker, Abir, Gallala, and briefly introduce her, and then give her space to present to you the topic entitled, or the talk entitled Structural Health Monitoring in Smart Cities, Building the Future of Resilient Urban Spaces. So Abir is not only a childhood friend of mine, but I also get to meet her, I don't know, I think over 20 years after, here at work within a European research project while she was doing her PhD in artificial intelligence and Internet of Things. So she also has a master degree in Internet of Things. She's currently working as a business development manager and AI specialist at ArcelorMittal. And with that, I would give you the word, Abir. Thank you.
Thank you, Hansa. Good afternoon, everyone. Thank you for the introduction. Thank you, everyone, for joining us today. I'm really glad to have this opportunity to present and deep dive into infrastructure monitoring in smart cities during this webinar. So let's start, but before we dive in, here is a quick look at what we will be covering today. First, I will give you a brief introduction to ArcelorMittal, just to give some context on who we are and what we do. Then we will go to or get into structural health monitoring. What is it, why it's important, and some of the challenges that come with it. After that, I will introduce a key technology that plays a crucial role in structural health monitoring, which is digital twin. And finally, we will look at a real-world use case to bring it all together at the end. So ArcelorMittal, actually, it's a global leader in steel manufacturing and mining, operating in over 60 countries and playing a vital role in major industries such as construction, automotive, and infrastructure. It's also at the forefront of innovation and research, working to create smarter and more sustainable steel solutions for the future. It has a deep commitment to sustainability. So we are developing cleaner steel technologies and striving towards the net zero emissions, all while maintaining the strength and the resilience demanded by the modern infrastructure. So through the cutting edge technology and innovation, the company is transforming the steel industry by creating advanced low carbon solutions that support more sustainable and future ready world. So just some highlights or glances on where you can find us. For the Burj Khalifa in Dubai, we produced 3K ton of beams in Differdange, Luxembourg. Also, you can find us in Venice, Italy, where we produced as well 150 kiloton of steel for the MOS. And also the Freedom Tower made of beams from Differdange, and some on the motorway. You can see as always sheet piles on the motorway construction. This is an example from Italy, underpass, and also another example from New York. The beams here produced from recycled materials from Luxembourg as well. So Luxembourg has long products and flat products segments, but for the long products, it's more for infrastructure, construction, energy, mechanical engineering, automotive, and so on. And we are from infrastructure sheet piling. So to understand what is steel sheet piles, actually these steel plates, let's say, interlocked all together, or interlocked steel sections together, used to build walls that retain soil or water, like retaining walls, cofferdams, foundation, also to provide strength and durability, and also very easy to install. So for sheet piles, we are producing in Luxembourg 2 mills in Belval, Differdange for hot rolling, and in Poland, Dabrowa mill, and also one in France for cold formed. For what we produce in Luxembourg and Dabrowa, Poland, different profiles. It depends on the size or the dimension of the profiles or the shape. So we have the AS flat or the AZ, what we call AZ, PU, or in Dabrowa in Poland, different GU, and in Differdange, the beams. This is what we call HTM, and also with different production capacities. So why we where or how to use these sheet piles produced in Luxembourg or in Poland? Actually, we have 5 main applications. 4 of them are permanent solutions. One for mobility, infrastructure, for water transport solutions like breakwaters, port key walls, and so on, hazard protection like dikes, and for environmental protection solution as well, to isolate some space area in the water, for example, or in the ground. So a few examples of our permanent structures. We produce sheet piles for retaining wall for metro line in Denmark. Here you can see in Poland bridge abutment, Poland as well key wall, and Germany flood protection solution and dikes. So both temporary and permanent structures are prefabricated products ready to be installed with a very high quality, fast execution, and a lifetime up to 100 years and above, and also recycled materials, so and then very easy to recycle and to reuse. What we also provide in ArcelorMittal, pre-designs, special piles, fabrication coating for some applications, and driven recommendation for the method, installation method, equipments, or some technical assistance as well at the job sites, and more services. Now let's move to the structural health monitoring, which is one of the services that we end up at the end. But let's understand what is structural health monitoring. So what we call SHM, structural health monitoring, is the process of implementing a damage detection and characterization strategy for engineering structures. It's the process that involves actually using or the use of sensors and the data acquisition systems, and also analytical tools to assess the condition of the structure over time, also to give some alerting to monitor the critical parameters such as deformation, stress, vibration, or corrosion, displacement, and more, and to provide insights into the structural integrity of the asset. So it's not only to enhance the safety of infrastructure, but also to reduce the maintenance costs by enabling predictive maintenance, and also to extend the service life of the structure. Then why we need such solution or such systems? The first always reason is safety of people and also assets, especially aging infrastructure that requires constant monitoring and maintenance. So structural health monitoring offers a cost-effective way to monitor the condition of these assets, and also to send or trigger real-time alerts related to operational problems or environmental damage. So also the structural health monitoring system provide early warnings and signs to weaknesses or, as I said, environmental events, to help to prevent the disasters maybe and minimize the damage by enhancing the decision making. Some other reasons, for example, I can mention increase the structure is a lifetime, expected lifetime, by tracking all the condition of the current condition and previous historical condition of the structure. At the end of the lifetime, we can decide if we can still really use it safely this structure. So then we are increasing the lifetime, the usage, and then addressing issues of scale as well. So by monitoring hundreds of kilometers or millions of structures, then if you have platform just to monitor this, the asset or the project owner not obliged to go there to check every meter or every pile or every section of the asset. Also the government regulation and the safety standards, because some governments around the world are implementing stricter safety regulations now for the public infrastructure. So for regular inspections and monitoring of critical structures like bridges or ports or dams. So such regulations are driving the adoption of structural health monitoring technologies to comply with these standards. Also, an important reason, actually, the cost reduction by removing all unexpected shutdowns or needs for maintenance. Then they have to close all the structure for a time, and this is can be expensive. So then the steps of structural health monitoring. The first step is we need to determine or define the damage that is existing now. So if there is a damage, we need to know about it. And then the second, to localize, means we need to know where is it exactly, on which section of the asset, and how much is it. Then we identify the effect of the damage, and then we take the decision or make a prediction for the remaining lifetime or the structural integrity, the status or the condition, the health condition of this asset. So how now, let's say, we are inspecting or monitoring the structure? One very traditional method is by visual inspection. So, but this method is somehow risky. It needs really labor-intensive work, and it's not something accessible for all the structure. Sometimes we have structure underground or in the water, behind the water, and so on. So these are inaccessible location that we can't really inspect. So we also need for this mission fully experienced people, and it's somehow subjective. We can't define exactly how much the damage is, and we can't cover all the sections where we have, or all the locations where we have the damage, and we need different technologies, actually, equipments, machines to do this inspection. And of course, it's very time consuming and costly, and we can't do it. Sometimes it's too late, so we really can't define the best timing to do that. Would be sometime too late to go into this inspection. So another method, it's a sensors based. We use real-time data collection. So there we embed sensors on the structure. We collect data in real time to prevent any event or any failure, to also reduce the maintenance costs. So the technology of the sensors can really be different from an application to another, and also with the improving of technology can be, or can have very advanced technology like smart sensors, and dedicated to either to each parameter to be monitored or to a group of parameters. We can also use wireless sensor networks, which is a bit challenging because the wireless, it's challenging in this condition because of the data transmission and the energy consumption, and also the reliability of the data. So it will remain a real challenge, except if we use sensors, wired sensors, or wired technologies, not wireless. Then the steps for structural health monitoring using sensors. First, the operational evaluation. We need to define what to measure, where to measure, how much, sensors, and so on. And then we implement the solution. We start the data acquisition from the sensors, we analyze the data, and then the features discrimination to use this information we are getting from the system. Some example of structural health monitoring, very important application could be offshore wind farms. The primary challenge here to deploy a structural health monitoring system in offshore wind farms is the environmental challenge and also the accessibility of the system. The dynamic load can be applied to the structure and also the power supply. So for this case, we can also use some edge technologies such as Internet of Things and artificial intelligence to enable real-time data transmission from the sensors using wireless networks, and this will resolve somehow the power supply, and also to support the remote monitoring by reducing the need for frequent on-site visits and inspection. Artificial intelligence can use machine learning to analyze the large data set of anomaly detection and then for predictive maintenance, also to identify the fatigue, the stress, and anomalies in terms of operational or environmental damage. Because here we, in this condition, it's a remote location that makes the physical inspection very expensive and difficult. The wind turbines experience a cyclic fatigue, loads from wind, wave forces leading to gradual wear and tear. And also the remote offshore sites require self-sufficient power sources such as energy harvesting sensors or battery-powered sensors, so some advanced technologies. Another example could be the bridges monitoring. It's very important to early detect the damage, to identify the cracks, corrosion, any unusual stress levels before they become very critical, because bridges here we are talking safety of people as well, not only assets. And then to monitor the traffic load, to record in real time the data on vehicle loads, to assess the structural performance and the different traffic conditions. This is also can be beneficial for governments to we were talking about standards and regulations. So one of these solutions for bridges for safety of people to use this kind of monitoring system or solutions. The environmental impact analysis. It measures the effects of temperature, for example, the wind, the humidity, stress, bridge structure, and so on. We also, it's very important to monitor vibration and analyze here the monitor of excessive vibration that could lead to structural fatigue or resonance failure. Maintenance optimization, of course, we want at the end to achieve or to provide actionable insights to plan maintenance proactively to reduce the downtime and also to save costs. Moving to one of the important applications that use monitoring, ports maritime applications. So stability and structural integrity, one of the most important objectives that we need to achieve using this solution to ensure the key wall remains stable and this any static or dynamic loads, because on the key walls also we have some heavy loads sometimes because of the containers and the ships, the cranes, the cargos, and so on. Here we can monitor the strain. We put strain gauges sensors to measure the stress and movements in the wall. For monitoring environmental impact, we want to assess the impact tides, waves, and key wall foundation of the structure. We monitor erosion and sediment displacement and other parameters. Also, it's very important to monitor the detection of deformation on the wall to identify the cracks, deformation on the structure at an early stage, because this is important to know this at a very early stage. And here we can use different technologies to monitor these. One of the solution could be fiber optic sensors for displacements and measure the cracks. One of the most important parameters to monitor in a maritime application, of course, is corrosion. So monitoring corrosion to reinforce or to predict the wall thickness of the wall thickness or the existing of any corroded area or holes. So there we put there are different technologies of corrosion detection sensors. So it could be, it's based on the technology. It either could be on the water side or the soil side. Then I want to mention one key technology that really plays a crucial role in structural health monitoring, which is a digital twin technology. And first, what is it for people they don't know? Basically, it's something that should answer on some questions. What is the activity, or what is the condition? What is going on there? And so we have what, where, when, who, and also why sometimes. So what is the current condition? Where is the location? Means if we have damage, where is the damage? If there is damage, where is it? And also when is it, when it started, and who made it? That's possible. We will see how to notice that. So it sounds like a foundation for decision making, and what to do now, what to do next. Do I have to tackle the problem which is visible in the digital twin, or looking for the long term? It is about events. So then we collect the raw data, we extract or get insights and context. So we transform the data to information. And let's say the most challenge maybe here, I think it's the problem in collecting the real and reliable data from sensors or from the physical twin or replica. That can be kind of tricky because it can contain anomalies. So at a very, or let's say, this is why we really need data analytics and advanced technologies, AI, to treat and analyze the data for fault detection as well. And at the higher level insights, first steps monitoring data, and then knowing what is happening and where it is happening. And then we can implement more platform for higher insights with more technologies. So if we want to categorize, digital twin can be divided into 5 levels. These levels represent the progressive intelligence of the digital twins and their interaction with the corresponding physical systems. So we can already see the 3 categories with the 5 levels. So the first category, which is also the first level, the digital twin, that we call the descriptive twin. So it's the digital twin where when it operates as a basic virtual replica or virtual model that simulates the physical object without automated data exchange, just the visual replica of the model. And then we have the second category, which also represents the second level, where it's called informative twin, and then where the digital twin at this level has a real-time data exchange from the physical objects to the virtual model. So there where we start to put the sensors to collect the data and to allowing the system to react to the changes in the physical objects. So then we can see them on the digital model. On the third category, where we have 3 levels: predictive, comprehensive, autonomous. predictive is where we use AI, mainly machine learning algorithms, to identify the patterns, to predict the future, to predict the events, anomalies, behavior, performance of the physical assets. So we know what is going on. Now we want to understand or to predict what will happen next. So at this level, the digital twin not only receives the real-time data, but also use all these advanced analytics, AI to predict the behavior. And then at the fourth level, to comprehensive twin, there we integrate also more AI algorithms, maybe to analyze historical data, to prescribe the solution, to recommend the future optimization with some situational awareness. And at the next or the highest level of the third category, the digital twin can learn and then can make decisions and also can take actions. This is the highest level, the most advanced, where the system is autonomous and on behalf of the physical asset and the users as well. So it's not applicable to all kind of applications. This is very unique or unique or dedicated for some unique applications. So as a recap for the structural health monitoring, especially about the digital twin, what are the real challenges that we can face? The first, I already mentioned a few of them, but let's just resume. Data availability. So to have the digital twin models, we really require or need to integrate the data sources. We need to collect the data from the physical asset and in order to analyze and to get the insights and the information. The better data we have, the better decision we can make and the better insights we can have. Better, I mean more data, but more reliable and good data. Then we have the complexity of the data integration, which this is more on the framework where we can lack the standards or the challenges on the integration frameworks. And then we have some technological advancements that we need to have high levels of digital twin. So there we really need to adopt and use innovative technologies and ongoing research. And honestly, we can't really achieve the highest level of digital technology. Maybe it's ongoing developments, and this is really depends on the innovation and ongoing research. And then we have the model verification, where after we not only create the digital twin, but also verify that it ensure what it's made of, and also to attend the service and the application at the end. Then we have the resource intensive for the after creating the digital twin, and then it requires substantial investment in tools such as very advanced smart sensors and technologies, platforms, finite element modeling, and to analyze and validate the behavior of the system. And these can be very sometimes expensive or not even available. So we could have even more challenges, but I tried to highlight the most existing or famous points. So I will move to a use case, which is related to steel sheet piles that I just presented, where we use exactly the same technologies in one of our solutions that we are offering at ArcelorMittal sheet piles. It's called Smart Sheet Pile. And there we use the structural health monitoring, digital twin, and all these technology to monitor, to detect, to predict, and to prevent the damage, also to know the current and the future condition. So similar or the same as the digital twin systems and the structural health monitoring, it needs to answer the following questions: what is the current condition? If there is any damage, where is it? How much is it? When it started? How much it will be in the future? The performance, the safety, and so on. So at the end, the solution will provide real-time monitoring of the assets and also alerting and notification capabilities based on the preferences or the specification of the project. Also, some added values that I think we already covered most of them. So it enables the safety first. So to detect accidental, operational, or environmental damage, early warnings. Also by knowing when we have exactly the damage, how much is it, and then we can schedule somehow or achieve the proactive maintenance, and that's how we really save money and time. So then we avoid all unexpected shutdowns, we save the cost with inconvenience, inconvenient maintenance. Also, by using this digital twin technology, we are really using the digital transformation, let's say, by having this multi-dimensional overview of the structure, the performance, the interaction with the surrounding. So it then acts as a very effective asset management. Some of the points that I think we did not mention, and it's very important to say, which is to reveal the hidden capacities. So if, for example, we have a port key wall, and then we can know the real capacities, the load applied, how much we can still use this key wall, how much load we can still put there, and then we really can optimize the usage of the structure. This is just an example, but we can reveal lots of hidden capacities and then maximize or optimize the usage of any structure at its full potential. And a point that I mentioned, which is the lifetime of the structure. At the end, we can really decide if the condition, with the current condition, we can still safely use the structure, and then we keep it for more few years than what was designed for. So how we achieve or how we implement the solution. So first of all, we can let's say it's not a standard solution, means for each application domain, for each project, it's a very unique solution, a customized solution. So for each, we need to study and design what parameters to be monitored, the business case and the strategy of the project, and the also preferences, what we want to monitor at the end. And then after making the detailed proposition with the sensor proposition, with the quantities of the sensors to be instrumented and all these details, we install everything, and then we drive the piles on the ground and we start the long-term follow-up. So there we can use online dashboards for monitoring. We can use or receive alerts when something is detected or predicted. We can use wired or wireless solution, and then we have some acquisition units to collect the data and to send it to the cloud. And from the cloud, we analyze the data, and then it just to feed either these AI algorithms or the dashboards or digital twin model and so on. Of course, we need to use bunch of edge technologies. Mainly, I can mention Internet of Things, AI, digital twin, and communication, of course, the big data analytics, because we are talking about not hundreds, not thousands, maybe even millions and more of data. So as I said, we need to define the parameters to be monitored and then implement that on the sheet piles, install the sheet piles on the ground, and then collect the data, store the data, analyze the data, process, and then feed the platform for real-time monitoring, digital twin models, and also for the alerting system or actions to be done and this is to be communicated to the end users. Coming back to what we can monitor, everything related to the core behavior of the sheet piles, means any parameters like the corrosion, position, displacement, deformation, soil pressure, shocks or impacts on the wall, the force or the load applied, and also anything related to the surrounding, means environmental information like water level, temperature, soil movements or inclination, and even more. So there we have different kinds of solutions, either wired or wireless. So wired, it's, let's say, in terms of data transfer and energy consumption, could be more stable, but sometimes it's more expensive to implement or more challenging to maintain the cables and so on. So maybe the wireless solution in some cases could be even better. And there we can use either batteries, solar power, or vibration energy harvesting for the sensors. Of course, each of these solutions has specifications and challenges. Then we made the first demonstrator where we have put some of the our sensor that we need for the monitoring, where we were able to monitor the corrosion by using different technologies like ultrasonic sensors, ER probes, ER coupons, also to monitor the inclination, deformation, the shocks, the water level. And then via the dashboard, we can see everything on real time. And if you want to deep dive into each of the parameters, we can go click on it, and then we can filter the data. We can see exactly, for example, for the shock detection or the impacts, we can filter the data. We can see how much is it when it started and where is it exactly. The same for all the other parameters, like the bending, the shocks, the water level, and so on. And then we went into a driving test. So we designed the piles, and then we went through a driving test. We installed the pile one time to the ground, and then we take it out and then put it again, drive it into the ground, and 3 times. And every time we check just here to check the reliability of or the resistance of the sensors and the cables. And then this was the first test with a vibratory hammer, and after 1 month after we left the pile half driven in the ground, we came back and then we finished the test with the more, let's say, hard conditions, using an impact hammer here, and then we measure again if one of the sensors, the cables were damaged and so on, because we well protect everything on the pile. Then we were testing, we were able to collect data from almost all the sensors. So none of the cables and sensors were damaged during the 2 phases of the test. Then we had the first project, which is a 135 long key wall, where we implemented 4 double smart sheet piles within 100 or more than 125 sensors, where we covered almost 10 parameters like corrosion, water level, inclination, strain, shocks, temperature, and so on. And then on the dashboard, we can read what is going on, the prediction, even the expected lifetime, material loss, and so on the different parameters, and then able to get alerts when something is detected. For example, if you want to get alerted when the water level is increasing, we will be able to see that or to receive alerts. Then we also use digital twin technology to use descriptive, informative, and to go towards the predictive twin, where we compare the simulated data within the the real data that we collect to make some predictions afterward. Well, I think this is the last slide from the use case. I will have some water, and please feel free to ask if you have any question.
Hi, thank you, Abir, for your talk. Unfortunately, most of the participants are over YouTube. I'm not sure if they will be able to ask questions or not. Maybe Teresa can confirm that or deny, but I'm not very familiar with the tool. We have also a few in this round that can also feel free to ask questions. Due to the delay on YouTube, I guess we give them a second or two. Otherwise, I have a few questions myself. I'm looking at YouTube here. Maybe something comes up.
Please go ahead.
Oh, YouTube can also ask in chat. All right. Okay, let's see. Until somebody asks something, I'll go ahead with the one question, more of like an on the non-technical side. So you were presenting systems of structural health monitoring, and I wanted to ask, how can you assess their role in climate resilience, for example, considering increasing weather events, global warming? How do you think this technology then can play a role, if at all, actually?
It's a very good question, because I think we are focusing too much towards climate resilience and climate change. So we are making lots of efforts to present our solution to resolve these issues. And also, we believe that smart and structural health monitoring smart solutions are very aligned together with the climate resilience. So it really plays a growing role in climate resilience. For example, as storms, floods, or any other events really become more intense. So then using structural health monitoring, it really helps the cities to detect the early signs, to get the alerting even before the damage or the fatigue, whatever is happening. So then it gives them enough time to take decision, the decision that they need, for example, to evacuate a place or do anything. It really, because it's really supporting real-time monitoring. So then it's the quicker way to be informed and then to make the decision, or the repairs, or the reinforcements, and so on. And it's good that on the backup I have something to show on this context. I hope I can play it. I hope you can hear it.
I do not see your screen anymore. I'm sure if you stop sharing.
It's not working?
I think you stopped sharing your screen.
Okay. Then just I will share again. Okay. I think now you will be able to see.
Yeah, we see something.
You hear it as well?
Yeah, we do.
Our world is fragile. But hope stands strong. Steel sheet piles can save lives. we at ArcelorMittal provide engineered solutions. Intelligent solutions. Strong solutions that will last for more than 100 years.
So I will stop it here, and I think we just made these to couple somehow our efforts toward the climate resilience efforts and also smart solution.
So just to follow up on this, the examples you mentioned earlier, and I think the whole idea is focused on more or less cities, like probably developed countries, but how do you see that on a smaller scale, like in developing countries or smaller areas where less people live, probably have less investment power and so on and so forth? What are the challenges that such societies can face in implementing this technology?
You said already one of the challenges, they have less investments. We are talking about costs, and that's true or correct that it's often seen as the cost has to be the biggest challenge, especially with the small cities or developing countries and smaller municipalities and so on. But let's say that upfront the investment which can be high at the beginning, considering the equipment, installation, the technical expertise, and so on, the needed for the project. However, if you look at it from the long-term perspective, the cost-benefit picture shifts then significantly. So structural health monitoring enables, as we said, proactive maintenance, the early detection of potential failures, even avoidance of catastrophic events sometimes by very fast decision making. So this really can save money down the line, far more than the initial investment, if we really make the calculation on the long term. So by catching the issues earlier, these cities or whatever agencies or municipalities can really avoid emergency repairs at the end, closures, shutdowns, even complete replacement of structure after the environmental damage, which can be really more expensive. So it's not only the cost there, we have also to look at it from another perspective, that also it has other added values beyond just the cost savings, just for example, to improve the public safety, people safety, increases the infrastructure lifetime, reduces the shutdown or disruption to the services, and so on. So it's really, as a long-term investment, it's not high cost.
Mm-hmm. So you keep mentioning the data being collected and so on. So there are probably different types of data depending on maybe which structure, which area, or is it a bridge, or is it something else? But how do you deal with this data? What type of data that could be? And of course, this data is being live streamed or sent. I don't know, each second, each minute. How do you deal also with data security in that case? Is it an issue?
It's not an issue, because for us it's not a problem, because we already have the solution. So the system that we provide for the moment really takes care of all these facts: cybersecurity, big data, the data transmission, the security of the cloud storage, also the prevention of any unauthorized access, and especially if the structure is really critical, because sometimes it could be transportation or energy sectors or related to governments and so on. So this is one of the important aspects that we really take care of. You also asked about what kind of data we are collecting, as I said, the types of data depends really on the projects. So it depends first on what kind of application domain. So maritime application, it's not the same needs as flood protection, for example. For flood protection solution, we need to monitor such parameters like water level, soil pressure, or other aspects. For maritime application, the port, we want to monitor the impacts on the wall, we want to monitor corrosion, and then it's very somehow the application domain and then also the preferences of the users. If they have very specific problems, then we really can target them.
Okay, I guess we have more questions. I see somebody typing in the chat. Please feel free to unmute yourself and ask your questions if you can.
Yeah, hello. Very interested in your talk. It's really very interesting. So I have some questions I want to know more. Right now, you said you are using basically use sensor to collect the data. So how reliable? I mean, you already mentioned, it is the issue of reliability, but how really reliable? And also, sensor are enough to collect all the data? Because for my understanding, so if you consider the sheet pile situation, so basically you want to detect the position. There are, for example, two sheet piles correctly hold together, installed together, and also if there are cracks on the surface or something like that. So my question is sensor is enough for that situation? Yeah, and also for the prediction, suppose the quality, the steel infrastructure, the quality is really good, and normally you don't have the abnormal cases. How do you deal with this situation? The last question will be how far the digital twin technology applied right now. So what are the advantages, compared to the current sensor-based or IoT-based technology?
Just if I go back to the third and the last questions, because for me, not seems to be very clear. So the last question, compared to what? You mean our current solution compared to? I don't get it. If you can explain that.
So what are the advantage to use digital twin compared to the current technology you are using based on sensor, based on IoT?
Okay, got it. Okay, then I will start with this question. Actually, it's not a separate or a different solution to be used. Actually, it's complementary. It means we will, of course, anyway, you need the same IoT technology and sensoring and so on. But then by adding more the digital twin, we can go to the next level. Means, okay, now we are collecting the data, we are getting the alerts and so on. But when we go to the digital twin, we'll be able to predict the events. Then we can really compare what we designed, the simulation on the finite elements and so on with what we are collecting from the real physical model from the project. And then we can go towards predictions and prediction. We will not go to autonomous in any way. Then I will jump to the second question. Then, as I said, actually every project is very unique. This is the word I like to use. Means we have to carefully study and also be advised and ask the advices of the experts and engineers that we have in-house to advise on the what to be monitored, how to implement the solution, how much we need sensors, where to put them exactly, and so on and so on. So it's not a standard that one sensor is enough. This is not we can't really, in some cases it could be enough, in other cases or other projects it's not enough, then we put more. This is
yeah,
up to me.
Yeah,
Okay.
I think so. That is the one of the solution. But what I mean is, so based on the data collection, suppose your system or your structure are really high quality, which means days and months and years, so they're really good. You know, you
Yeah.
receive a very normal data. How do you do in that case?
We always have the solution, we always have the system. Sometimes monitoring, it's not about the quality of our sheet piles or our solution, but also for environmental impacts. We want to monitor the increase in water level to know if a flood is there is a flooding coming, for example. So this is nothing to do with the quality. And then, yeah, we have always this probability of having deformation in some cases based on the load applied or the vibration, whatever. It depends on the solution. So the quality of our product does not really means that we don't need this solution of monitoring. Monitoring in any way, it's something that we have. It's not related only to the operational or the behavioral of the structure, but also to the surrounding, to the impacts of on the wall from the ships, for example, on the increasing water level, on the soil movements, on the temperature, on the load applied, on the ice loading sometimes. So this is very important to monitor.
Yeah, that is for the monitoring. Thank you.
Did I answer it all to your question?
Yeah, I think so. Maybe we can give the chance to the others.
Okay.
So I'm checking on the chat on YouTube. I see no questions, so I'll ask again in this round if somebody has further questions. It does not seem like it. So in that case, well, thank you again, Abir.
Just one comment, if you don't have more questions. So I don't see the name of the person who just asked the question, sorry, but in any way, I think here, I think you have my contacts information, email. So if you want really to know more or to discuss more, please feel free to contact anytime.
Actually, this is what I want to do. And how to pronounce your first name?
I can put it on the chat.
Okay, so how to pronounce? I want to call you.
My name?
Yeah, the first name, how to pronounce?
Abir. It's Abir. Yeah.
My name is Xia. Yeah, okay. Nice to
meet you. So there I've put it on the chat. Yeah.
And great. Thank you for your time, Abir. Thank you for doing this with us. Yeah, I think I'll wish you all a nice afternoon. Enjoy the sunny weather and see you in the next round.
Likewise, thank you very much. It was a pleasure for me to really be here and to present today. Please feel free to contact me anytime. You have my email address. And good afternoon. Enjoy your day.